Hi everyone. So today the topic of this lecture is on hydraulic jump. Okay, this is the figure of a hydraulic jump. Okay, this is taken from the textbook, figure 3.1. Okay, first you have to notice the sluice gate. The sluice gate followed by a hydraulic jump. Okay, so we have four different types of depth here. First, y1 and y2, yc and y3. Okay, y1 and y2 are alternate depth, while y2 and y3 are known as conjugate depth. Okay, so the flow is moving from left to right. Okay, so one important message, one important concept in this case of hydraulic jump is first the conservation of energy. Okay, energy is conserved between point 1 and point 2. Okay, which is E1 is equals to E2. And here it is called alternate depth. Y1 has subcritical flow and Y2 has supercritical flow. Okay, for subcritical flow, the Froude number is less than 1, and for supercritical flow, the Froude number is more than 1. Okay, so we have another situation here, which is conservation of momentum. Okay, conservation of momentum occurs in this section. Okay. Okay, here we have conservation of momentum, but in this section we have so in this section we have conservation of energy. Okay, for the conservation of momentum, we call this y1 and y2 and y3 as conjugate depth. So y2 has supercritical flow, which is the Froude number is more than 1, and for y3 it is subcritical flow, which has Froude number less than 1. Okay. You also can observe that y3 here. Okay, here is y3 and here is y1. Okay, y3 is less than y1. So it means there is energy loss occur within the hydraulic jump. Okay, so for loss of energy in hydraulic jump, it can be written as this. So E1 is equals to E3 plus HL. HL is energy loss. So the equation of energy is Y3 at section 3. Yeah? Y3 plus Q to the power of 2 divided by 2GY3 to the power of 2. Okay, plus HL. So, according to the textbook, HL in this case can be described by momentum equation. So we will see later how this energy loss occur and how momentum conservation of momentum is described here in the hydraulic jump. Okay. Okay, from this slide you can see the figure of sluice gate and also hydraulic jump. Okay. So it's just a matter of numbering. So now from the previous figure we have, this is y1 and this is y2 and this is y3. Okay, so if you follow the conservation of energy, so energy depends only on location. Okay, so it's a scalar quantity. However, for conservation of momentum, so momentum has its directional nature. So it's a vector quantity. Okay, so the formula is like this: momentum is equals to mass multiplied by velocity. So it has this direction, okay, because momentum and velocity has the same direction. So this is mass and this is velocity, okay. Okay, downstream direction is taken as downstream to this direction is taken as the positive direction. Okay, so from the textbook, the units of analysis is modified from momentum to momentum per unit of time. So this momentum per unit of time is also known as momentum flux, which is simply known as force. So force is equals to mass times acceleration. Mass, yeah, this, and times acceleration. Okay? Okay. So there are two kinds of forces associated with flow in open channel, which is static and dynamic forces. So this is the equation, the formula for static force, gamma W multiplied by y to the power of 2 over 2. And for dynamic force, the equation is rho times Q times V. Okay? So this is y, the depth of flow. Okay? Okay. So momentum is equation in this case is equals to force, static force plus dynamic force. So it follows this equation. So this is equation 3.5 from textbook. Okay. Okay, so by this addition of two forces, you simplify this equation further by dividing the equation with W and density of water, and you have this equation, is equation 3.6. And further, you further simplify this equation by putting m on the left side. Here, this is momentum. And then v is substitute with q over y. So, you will get this equation finally. Okay, so this is the equation for calculating momentum in open channel flow. Okay. Okay, now we have two different figures. One is associated with energy. So this is the energy EY graph or specific energy graph. You can also call it specific energy graph. Energy graph. Okay, so in the y-axis you have depth of flow, depth of channel, and on x-axis you have energy. Okay, so you have seen this specific energy figure before this from the previous lecture, right? Okay, so I also gave you some of the observation that you should see, that you should observe, okay, from this figure. Okay, now we also have another one is momentum graph. Okay, momentum. Okay, so because here this is momentum, and here is depth. Okay, so this curve inside, this is Q. So this is increasing Q. So we have Q2, 3, 4, and 5. So 2 is here, 4, 2, 3, 4, and 5. Okay, so here also you have Q, 2, 3, 4, and 5. Okay. Okay, so you also can observe the minimum value of momentum in this figure. This is the line of minimum momentum. Okay. Okay, so in this figure of energy, you can also observe minimum value of energy. Okay. So both EY and MY relationships have similar shapes. Okay, so you can see these similar shapes. A subcritical and supercritical branch. Okay, so you have the upper part is the subcritical and the lower part you have supercritical. So it's the same here. This one is sub and this is supercritical flow. Okay, and both curves shift to the right as Q increases. Okay, you can see this, and both curves reach a minimum. As I said to you, this is the minimum for momentum, and this is minimum for energy. Okay. Okay, but there is also some differences between these two graphs. For example, there is no analog to the y equals E asymptote in this momentum. So for this asymptote, you know, right? This is the asymptote part where E is almost equals to y at certain value, right? But in this case, there is no such thing. Okay, in the momentum graph, it doesn't have any asymptote value. Okay, and the curve that passes through critical depth is not linear, but instead is given by the following formula. Okay, what it means is that here the relationship is linear, where you can find y is equals to 2/3 multiplied by E. But for the case of momentum, the relationship is somehow quadratic. Yeah, you see here, this one for this value. So here y critical depth, okay, critical depth, which is yc, is equals to 2/3 times minimum momentum square root. Okay, square root of 2/3 momentum, minimum momentum. Okay. Okay. So from the previous slide, you know that the equation of my momentum is equals to y to the power of 2 divided by 2 plus q to the power of 2 divided by gy. So y is the depth of the flow open channel, yeah, and q is the flow, unit flow. Q is equals to q divided by width. Okay. Okay, so you can find this equation in equation 3.7. Okay, so you already know that here in this section, what is conserved? Momentum is conserved. Okay, so y2 m2 is equals to m3. Okay, so we use this equation of m at position 2 is equals to m momentum at position 3. So you have this. So this is momentum at location 2 minus momentum at location 3, and then you get equal to 0 because this is actually equals. Okay. Okay. So finally, when we simplify this equation, we can get y2 is equals to this equation, y3 to the over 2 multiplied by square root of the whole equation here minus 1, or it can also be written as Froude number. So because you know the Froude number is equals to q over g y, right? Okay. Okay. So yes, our interest from this situation is we always want to know what is y1, what is y2, and what is the critical depth, and what is the y3. Okay, for this situation at y1 and y2, you can use energy conservation principle to determine y1 and y2, energy conservation. Okay, in the case of y3 and y2, so here you use conservation of momentum. Okay, so we will do this exercise, and then you can see how can we use this equation and also equation previous equation from energy, to find Y, to find E, and to find momentum, and we want also to find Froude number, because we are interested with the types of flow, whether it's subcritical, critical, or supercritical. We know it already by theory, and we want to learn how to calculate them. Okay, so see you in the next video. Thank you.